recall that what we talked about last time. Let's recall the comparison theorem. So let K be a complete discrete valence field of mixed characteristic. And I want to assume it's absolutely unramified and with perfect residue. And I want to assume that my X is proper smooth over OK. And then last time we discussed that we have a comparison that taking the étale cohomology with QP coefficients of mixed characteristic 0p, so residual characteristic p. This would compare well the so-called crystalline cohomology. As I said last time, we don't have to know too much about what really crystalline cohomology is. And it's also can be also identified, because this one really can be identified with the Ram cohomology. And the étale cohomology and the Ram cohomology and the crystalline cohomology, they can be compared if you tensor this all with the period ring B Chris we discussed, we introduced last time. And let me also mention that on the left-hand side, if I take Galois invariance, this étale cohomology carries a Galois action, whereas B Chris carries a Frobenius and a Galois action and a filtration on that. And same here. And this crystalline cohomology has a Frobenius action, whereas this, if I identify it with the Durand, this one has a filtration on it. So this isomorphism is compatible with the Galois action, diagonally acting on both factors, and on the right hand side, only on the right hand side. And then it's also compatible with the Frobenius action, which is only on this factor here, and acting diagonally on these two, and filtration, which is sort of combined filtration of the two. And moreover, if we take the Galois invariance, so what's going to happen is that it will, on the right hand side, it will kill this B Chris term and left with this crystalline H Chris. So taking Galois invariance gets H gives this HI Chris of X OK with P inverted. So this guy is left with a Frobenius and a filtration. And similarly, if I take phi equals 1 part and then field 0 part, I can recover somehow. Basically, that will kill the B Chris part, and I will get back my HI étale. So in a sense, when this X is a proper smooth variety over OK has a good reduction, the situation is particularly nice that somehow the crystalline cohomology together with the Durand cohomology altogether that has the same information as the étale cohomology. What we want to do today is, first of all, to give a purely Galois theoretical version of this. Namely, So now I want to start is, what I want to start is a continuous periodic representation. Or sometimes I want to think of it as a Galois group K acting on V. Maybe I'll kind of make a quick remark that typically rho of IK is huge in GLN. So when we talk about L algebra representation, well, L not equal to P. So the image of the inertial subgroup is very easy to control. The reason is that maybe I should say well inertia. In that case, well inertia subgroup, because it's always pro P, and if I talk about L representation, this side is mostly pro L. In some sense, these two are not compatible. So therefore, the image of the well inertia is always finite. But typically, for a P-I representation, this is huge. This well inertia has a huge image in GLN and QP, and typically, very often surjected onto GLN, not GLN Q, but GLN Z because it's compact. So so somehow, obviously, we can't deal with this using the same method we were dealing with L representation. We need some sort of new method. So that's what we're going to be doing. So we're going to be mimicking what we have over there, in the sense that I want to think of this Italian cohomology as the Galois representation V. And I want to sort of do the test with V Chris and go to the other side and get some information there to store there. And that also allows us to come back later. So what I want to do is I want to define that D Chris would be V tensor with V Chris. And I kill the Galois. Just like what we did over here, that if I have my V being the Italian cohomology, and tensor with V Chris, if I kill the Galois cohomology, I'll be getting this sort of crystalline cohomology if this V does come from geometry. Of course, in general, V does not come from geometry, but this is still well defined. So this one, as we had over there, we have this Frobenius action and carries a filtration. Just emphasize it carries a decreasing field. So here's a fact. It's not too difficult to prove that this decrease V is always a finite dimensional K vector space of dimension less than equal to the dimension of V as a vector space over QV, namely. And we say that V is so-called crystalline if, I'm making a definition, I don't have to write if and only if. Anyways, if and only if this dimension is just literally correct. So the equality is cheap. So in this case, so-called Hochschild weight I'm going to write that HT of B of V are the integers Note that my decrease of V carries a carries a decreasing filtration. So I can ask where the filtration drops. So that's where those numbers are precisely the Hartree weights. In other words, the Hartree weights are the numbers I such that the gradient piece of decrease of B is not 0. And I want to think of this Hartree weights as a multiset. Namely, it's a set where elements can have multiplicity. So namely, counted with multiplicity being a dimension of the gradient piece I of decrease. So I just want to give you, so this is how we define decrease. It's a little bit, it feels like it's a little bit empty. I don't know. I don't know how to think of this. Maybe, let me give an example of how to think about how to think of this Kristallin representation. In some sense, the thing I want to convey is that in the p-adic world, Kristallin representations look a lot like unramified representations in the Li setting. So here's the fact. If A is an abelian variety over K, then the following are equivalent. This A has a good reduction, meaning that if I have a proper smooth abelian variety, A over OK, such that I can, such that my generic libraries are given A. This is some geometric property of the abelian variety. But this geometric property can be seen from étale cohomology, the first étale cohomology of the abelian variety. So for some or any L not equal to P, the H1 étale cohomology is unramified. In the sense that this first étale cohomology carries an action of the Galois group of K, and we're going to probably say this next time that in general, if you have a variety having a good reduction, then the corresponding étale cohomology will be an unramified representation of the Galois group. But conversely, if A is a abelian variety, this can go back. In general, it's not. Well, in general, probably not true that the étale cohomology being unramified implies this A has a proper smooth reduction. That's probably not true in general. But for abelian varieties, it's true. And analogously, this is a situation where L not equal to P. But when L equals to P, the corresponding statement is that this is crystalline. In other words, one should really think of for p-adic representations, crystalline is the same thing as being unramified. But of course, crystalline representation has some additional information in it, besides the information about the unramifiedness. Namely, it also contains information of the Hartree weights. In other words, in this case, the Hartree weights of this thing will have. I mean, it's always. This guy has always dimension equal to, say, 2n, or excuse me, 2n, where n equals the dimension of A. So this is a 2n dimensional QP vector space. If you take decrease of that, it will carry a filtration, and the corresponding Hartree weights will have 0 and 1, each with multiplicity n. So it will contain a little bit more information than this. And also, kind of to echo what we recall last time, that when x, this way, x is proper smooth, or okay, I can do decrease of the ith étale cohomology. that's just precisely, we just precisely get the crystalline cohomology. That's basically what we get from the comparison theorem over there. Okay. To continue on with this comparison theorem, remember that all we're doing right now is that we started out with a representation on the left-hand side, and I apply sort of representation here, and I test it with decrease, and I get, taking Gaussian invariance, I get something with a Frobenius action and a filtration. Somehow this can go backwards, just like what we have for the comparison, right? I mean, I can get the H crisp from the H etal, and I can now get H etal from the H crisp. So if V is a crystalline representation, then V can be recovered from this decrease. By taking V equals 1 and take the part that's field 0. I mean, if you don't like this sort of comma field 0 part, you can say, okay, this intercept is field 0 of the entire thing. Okay. If it needed to be, maybe let me sort of explain a bit more about what I mean by this field 0, this one. So this field 0 means that it's the sum of I plus j being 0 of field I decrease of B, and so it's field j of decrease. So when you have two filtered, filtered vector spaces, their tensor parameter has a filtration. Then we just sort of capture the corresponding filtration and sort of sum them up. And so right. So if you have, so this basically gives us a way to, in terms of describe crystalline representations. Somehow, I guess, or put it another way, somehow. In the sense that if you have a crystalline Galois representation, I can test it with decrease, and I get this sort of this sort of Frobenius action together with the filtration. And once we have this, we can recover my representation B. Now it's very natural to ask, so suppose I don't have a representation to start with. I just have a phi, just have a vector space with phi action, and I have a decreasing filtration. And can we recover a representation out of it? Actually, before that, I have to point out one thing I kind of missed here. Because I'm dealing with general K here, I have to be a little bit careful here. So, right. So let's, I also need the same assumption as before. So C is the complete valuable field, absolutely unramified. That's still in place. And this thing is a K vector space. And the phi action on this is really truly the Frobenius in the following sense that, so phi action is, I should really point it out, I forgot, semi-linear. In the sense that phi of A, M, equals phi A, phi M, for A in K, and M in this decrease. Okay, I forgot to say this. The phi action here is really semi-linear, not linear. But of course, in our later application, my K will be QP. Then the phi action on QP is trivial. So it really becomes a linear action. So that's why I kind of forgot it. Okay. So now, let's come back to my question that this decrease of V carries a semi-linear action of phi and a decreasing filtration. And then to ask if I just give a sort of random K vector space with a semi-linear action of phi and a decreasing filtration, does it come from a representation B by taking decrease? So the answer is the following. Moreover, there's an equivalence categories. This category also compatible with tensors and duals. Let me write this equivalence up here. I don't think it will fit over there. So it will be an equivalence category between crystalline representations of Gauss group of K with something I'm going to call admissible filtered phi modules. Somehow the filtered phi module part is sort of self-explained. Namely, it's a sort of finite-dimensional K-vector space with a semi-linear phi action, and together with the decreasing filtration S we had before. Basically, I just need to explain what this admissible means. This will take a bit of time. So let's see. So this is equivalence. So namely, those filtered phi modules that satisfy certain conditions we're going to specify later will be those corresponding crystal representations. So this gives a way to describe all possible crystalline representations. Or in some sense, if you have some sort of geometric object proper smooth over OK, this étale homology will be of this kind and can be classified using such filtered phi model. So this is given a sort of, in sense, this crystalline representation is very complicated. You don't know. I mean, it's really difficult to talk about its image of, say, the wild inertia or something. But then on the right hand side, this object is much easier. There's a phi module, just a phi action, and it's only a filtration there. So that's it. So that makes it, I guess, description of the representation a lot easier. So let me be specific about filtered phi module. So that will be a D and a field D, where D is a finite dimensional K-vector space with a semi-linear phi action. And this field D is a decreasing filtration. Satisfying a weakly admissible condition. So let me explain the weakly admissible condition here. So I need to introduce two quantities. When the dimension of this vector space B is 1, so basically, in some sense, so this D is just simply a K-vector space with sort of one basis E. Now I know I can look at this, how phi acts on this E. It will be, scale it by some K. Oh, and maybe I should also require, hold on a second, with semi-linear actions, and this phi is bijective. I don't want phi to act to sort of. I don't want phi to be just to be multiplication by 0. So therefore, in this case, I guess one other case, so phi e will be equal to alpha e. Then I define the Newton weight or Newton whatever. It's a periodic evaluation of this arc. So this N for Newton. Okay? So let's check that this is well defined. So if I have another E prime, I mean, it's a one-dimensional vector space. I have I can choose a different basis. So this is equal to E beta. Then, if I do phi E prime, this will be equal to alpha times, let's see, right? You must have beta of phi of beta. Okay? So this is a Frobenius action on beta. So somehow, because it's semi-linear action, you really can't talk about eigenvalues. Nonetheless, the periodic evaluation of this thing is a well-defined number, because Frobenius action will not change the periodic evaluation. So therefore, you have this. So in general, I want to define the Newton number, Newton number of a D to be Newton number. I can take some exterior power of this D. Top exterior power of this D as vector space over it. Okay, and this exterior power will carry a semi-linear action of phi, and that I can define a number. So I just define it like so. So that's half of the definition. So this is the Newton part. And then I remember that I have a Hartree weights. So Hartree weights give me another number called Hodge number. Similarly, I can define Hodge of D. So this is a Hodge to be the sum of I of dimension of graded I of D. So this is the sum of all Hodge weights. I mean width of this thing. Okay. So now we have two numbers, Hodge and so we say that D is so-called weakly admissible. Oh, right. I forgot to explain that. Over there I wrote down admissible filtration, and over there I said weakly admissible. So there's no difference between the two. The difference is historical. So historically, this equivalence category is a very hard theorem. So when they define things, they define this weakly admissible condition over here, supposedly to be So they define these weakly admissible conditions as we're going to define here, and the admissible filtrations are those that does come from representations. The conjecture at the time was that the weakly admissible is equivalent to admissible, but this is now a theorem. So now we don't have to distinguish two things. So weakly admissible condition is sort of the same thing as admissible condition. So namely, if the filter phi module satisfies the weakly admissible condition, then it must come from a representation. So there's no difference anymore. But in the past, I guess people talk about these separately, and therefore the names are passed on. So we say D is weakly admissible if TH, the Hodge number and Newton number for D are the same, and for any phi stable sub-K vector space, D prime of D, the Hodge number must include the Newton number. Newton about Hodge. So Newton D prime. And just want to remark here that for Newton number there's no problem because D prime is phi stable, so you can define the Newton number for the D prime as usual. But then for the Hodge number, I want to point out that this is using the induced filtration, i.e. that I define filtration I of D prime to be D prime intersect with field I of D. So that's namely the filtration on D prime is the one that's induced from D. So for that filtration, the weakly admissible condition says somehow the Hodge number is less than or equal to Newton number. That feels a little bit too abstract, so let's give some examples so that we can calculate the more explicit one. So say I take the one-dimensional representation, cyclotomic character representation, to tensor with itself nth power. Okay? So in other words, my representation V is QPE with the Galois group element G acting on E to be chi-cyclotomic of G nth power times E. Okay. So scale it by cyclotomic to the nth power. Let me point out that cyclotomic character has image ZP cross. So therefore, this has represented with a large image. Especially the wild inertia will have a large image because wild inertia is basically the part which is 1 plus PZ inside it. Okay. So let's see. So I have decrease of B. Let's compute decrease of B. What do I have? I have QP. I want to tensor with B Chris, right? And then I want to take Galois invariance. Okay. So what is this? So let's, in fact, there are two things. First of all, this is one-dimensional. So therefore, by our general fact that this is at most one-dimensional over K. Let's find an element which is invariant under Galois group of K. So recall that in B Chris, there's a particular element called T. Namely, this G acting on T is cyclotomic. Cyclotomic of G times T. So this actually is precisely the same thing as E. I mean, up to some twist. So therefore, you can easily see that if I take E tensor with T inverse n, that's going to be invariant under the Galois action. So for very precisely, I have this decrease of B being that one. Now what are the actions? So I have the phi action on this particular element. So phi doesn't act on the basis of this Galois representation. Phi has no action on the Galois part. But then phi t is equal to pt. So therefore, this is p to the negative n times e to the tensor with the inverse. So therefore, the Newton number. Oh, sorry, this t is different from this t. I don't know. All the references I've seen, they use Tn for the Newton number. I don't particularly find it. Anyways, so this is minus n. Okay, so what about Hodge tape? Weights or the filtration. So recall that the filtration comes from embedding your B Chris into B drum, and over here, this is the completely discrete element field with T as the uniformizer, and the filtration on B Chris or on B drum is given by the valuation filtration. So therefore, what we can say maybe for this valuation, I do this element, t to negative n, right? So this valuation is negative n. So we know that if I do filtration of I, or rather this tells me that if I do E tensor with t to negative n, this must be in the degree negative n of the filtration. In another way, this is, excuse me. Oh, I should write decrease of this. So therefore, this is equal to the entire thing. If I is greater than or equal I equals n negative n being the sort of the changing point. So this tells us that Hodge number of this is negative n. We see that for this particular case, the Newton number and the Hodge number are equal. So that's a weakly admissibility condition. The weakly admissibility condition. It requires the Hodge number being the same as Newton number. But in this case, there's no sort of phi-stable sub-K vector space of D, except for 0 and D. So in this case, this condition here is, you don't see this condition here. Let's give a, before that, let me make a remark that, so when you go to talks, so people use somehow for this hot-take weights and then these Newton numbers and Hodge numbers, people have various different normalizations. Personally, I think this definition is sort of, I guess, used by more people, a larger percentage of people using this notation. But one of the important questions you ask, so that you make sure that you're using the same convention, is that the hot-take weights of a cyclotomic character is negative 1. So for our convention, the hard-take weight of a cyclotomic character is negative 1. I understand this is a little bit of a, sometimes you want a hard-take weight of a cyclotomic character to be 1, so that you think it should be 1. This one negative weight is annoying. But it seems to me that, I don't know, this is the convention I'm using, and I feel that this is a convention more people are using. Okay, so let me give you another example of this weak admissibility condition. So let's take a module 4. So of level gamma naught n and weight k. Okay, I'm going to assume that P does not divide. And for simplicity, let's assume all ANs are rational numbers, or rather integers. I mean, if they're rational numbers, then we know all these ANs must be algebra integers, so they must be all integers. Right. So let alpha and beta be zeros of the polynomial x squared minus apx plus p to the k minus 1 equals to 0. So this is usually called the Heck polynomial at p. So this AP is the eigenvalue for the TP operator. So you're doing x squared minus APX plus p to the k minus 1. So the two roots will be important for us. And because this AUP now is an integer, and also let's say alpha not equal to beta. Conjecturally, this is always the case, but I guess it's very difficult to prove. Then, at least it's not that difficult to show that you see that this is integral, and you probably have done some of this Newton polygon, PI Newton polygon stuff to know the valuations. So you know the PI valuation of this too. First of all, these are integers, so therefore they must be non-negative. On the other hand, alpha times beta is p to the k minus 1, so therefore the two valuations adds up to k minus 1. If both of them are non-negative, then they cannot go over k minus 1. We'll later on talk about the discuss more carefully about the Galois representation attached to modular forms. But right now, let's sort of just accept the fact that this will give us a representation, or a continuous, of course. And of course, I can restrict it to the Galois group of QP. And so take this as a fact. This rho f is a crystalline representation. Rho f, we call it P. So this restriction is called rho f, comma P. And this is a crystalline representation. In a sense, because P does not divide the level n. So if we were talking about analytic representations as a place P, if P does not divide the level, the corresponding representation will be unramified. But now we're in the p-adic representation, and P does not divide level, so unramifiedness will be turned into crystalline representation. This is crystalline representation, right? And moreover, this decrease of this can be written as follows. You have two, because it's a two-dimensional representation, if it's crystalline, then the decrease of this is going to be two-dimensional. So we have two bases, E alpha and E beta. We can always choose the basis so that for Venus action on E alpha, for Venus we'll have two eigenvalues, namely the two roots, alpha and beta. So I take the corresponding eigenspaces, as so. And therefore, from this, we deduce that the Newton number for decrease of rho fp is equal to the sum of two valuations. That's just k minus 1. And I guess because we know that this is something that does come from a representation, so we know that Hodge number will be also Hodge number will be also k minus 1. Indeed, the two Hodge weights are 0 and k minus 1. So phi I of decrease of rho fp is equal to decrease rho fp if I is less than or equal to 0. 0 if I is bigger than k minus 1. So in the middle, so basically there's two jumping points, I equals 0 and I equals k minus 1. And the middle thing will be a one-dimensional space. So there are essentially three possibilities. If you think about what are the one-dimensional subspaces of this one, right? It could be QPE alpha, or QPE beta, or I mean, it could be a linear combination of E alpha and E beta with neither coefficient being 0. But of course, I can scale my eigenvectors by a scalar so that I just precisely E alpha plus E beta. So basically, there are three cases. In any case, this will tell us that the TH, the Hodge number, will be k minus 1, because two Hodge weights are 0 and k minus 1. So let's discuss the divisibility condition. So admissibility. I said, okay, are not equal to beta. So, okay, admissibility. So Hodge number is equal to Newton number. That's good. But then we'll have to check for all phi stable subspaces. So there are two phi stable subspaces, namely QPE alpha and QPE beta. So we know that Tn, so let me take just one, I mean, because I guess alpha and beta have this symmetric position, right? So let's just take alpha. So the Newton number for this is just precisely the p-adic valuation of alpha. Whereas Hodge number, well, it depends. Well, it depends on which filtration we're looking at here. So if the filtration is E alpha, then we see that the filtration is what? The filtration is the whole thing if I equals 1, 2, all the way to k minus, and also less than 0. It means the filtration on QPE alpha will be intersection of the filtration with QPE alpha, this one-dimensional space. So when you do the intersection, if this filtration takes this case, then the filtration will be sort of the entire space for I less than equal to 0 and all the way to up to k minus 1, and changes when this k minus 1. So in that case, Hodge number is k minus 1. If this, just basically I just look at field 1. Takes to QPER. In all other cases, if this filtration looks like this, then when you intersect with QPE alpha, it will be 0. So that means that this filtration for QPE alpha will be sort of 0 unless I is less than equal to 0. So the jumping point is I equals 0. So you have this dichotomy here, depending on which filtration you take. So in the strand case, when the field 1 is QPE alpha, this admissibility condition implies that what do you want? You want your Hodge number to be less than equal to the Newton number, so that you want k minus 1 to be less than equal to the p-adic evaluation of R. So in other words, if this filtration is sort of purely concentrated on one of the phi eigenspaces, then eigenspace, then this eigenvalue of alpha will have very large p-adic evaluation. Remember that the sum of the two p-adic evaluations is k minus 1. So this will imply that p-adic evaluation of alpha is p to the k minus 1. And at the same time, p-adic evaluation of beta is 0. K minus 1. So this is a sort of strand case. In the other case, in the other cases, this admissibility condition implies that the valuation is greater than equal to 0. This is automatic. So that's the only this is sort of the example I want to discuss, that to see what this admissibility condition is. And this is what's really happening for a modular form F. It may have, so for most of the cases, the p-adic value of the two the two zeros of the Hack polynomial will have sort of valuation between 0 and k minus 1. If the filtration is sort of strange in such a situation, then one of the valuations must be precisely the upper bound, k minus 1. The other value must be 0. This is so-called critical case. This is called critical case. So in p-adic, this is called critical case. So we're not going to discuss too much in here. So that's kind of a discussion of crystalline representations. So after discussing crystalline representations, now I want to switch to the next step to talk about integral theory. So this is the so-called Fontaine-Laplace theory. this is integral version of it. The reason we want to talk about this is because we want to talk about deformations. Where deformation always starts with the residual Galois representation, mod P representation. And all our discussion have been starting with a representation with PID coefficients, QP, but not mod P. So there's a bridge we have to, there's a gap we have to bridge, right? So this is, so what we're going to discuss is a sort of simplified version of this. You probably have seen people talking about Schultz's work with integral PID Hawk theory. This is a much easier version than that. This happened way before that, I guess. So, right. Another thing I want to make a remark is that we'll work with ZL coefficients and the representations of the Galois group of QL. I apologize for somehow switching L and P. For PID Hawk theory, I guess we're all accustomed to talking about PID coefficients. But since later on our application is to talk about L-ladder coefficients systems and L-ladder coefficient representations, so I'm going to switch back to L. So we'll only discuss the case K equals QL. The general case is more complicated. So, and also allowing coefficients to be O. So this is a Riemann linear in the E, which is finite extension of QL. So earlier when we talked about decreasing stuff, when we talked about QP coefficient, it's not that difficult to generalize to the general coefficients. But there are some subtleties I'm hiding here. So, I guess sort of inspired by this sort of picture of correspondence between crystal representations and filter phi modules, what we're going to do here is that we're going to talk about sort of integral lattices in the crystal representations corresponding to some sort of filtered phi modules with some additional structure. So that's the idea. So definition. But this will be integral version of that. So let MF. This is in French. This modulus filtré. French. I guess it's named after, Fontaine Lafayette called this. So. You know the following category. So let's see. So what are the objects? So basically, I need a kind of replacement of filter phi modules. So I need an integral version of that. So the objects are the following. So M consists of filtration of M and phi I. So three things. This is called a Fontaine Lafayette module. Where I want my M is a finitely generated O module. Okay? So I don't need to be free. It could be torsion, and typically torsion, I guess. And I wanted this M to have a filtration. That looks like the Hodge filtration. As we did before. But of course I don't want it to be filtered by L times M. and L squared times M. I don't want that kind of filtration. So what I want is that each field IM is an O modular direct summand of M. Namely, I don't want filters like L times O inside O. I don't like that. And also I want additional filter. I want to confine my Hochschild numbers. I want field 0 of M to be M, and I want field L minus 1, the L being our L there, and M to be 0. So this will imply that all the Hochschild weights we see are in 0, L minus 2. So this is essentially a kind of this is an essential constraint of the entire theory. This Fontaine phi theory is very nice and very, it's a very heavy theory, but then except that the Hochschild weights number will never get beyond L. But for our later application, when we actually do this Fermat's law theorem's proof, Hochschild weights will be 0 and 1. So I need to take L to be greater than equal to 3. That's enough. So that's enough for that purpose. But for later generalizations, this for generalization to more general orthomorphic representations or orthomorphic forms, so that's going to be a big problem. So what can I use that? Well, it depends. So this basically says that the L, the coefficient L, has to be greater than, to be sufficiently large. Okay. So now, I also need an O linear map. Well, before I write down what such that means, such that what it would do, let me say what this means. I want it, so this will be phi divided by L to the I. Okay? I want my phi to be some phi divided by L to the I. But then the problem is that my M is to find a general O module could be well torsioned. So it does not make sense to say phi divided by L to the I. So the only thing we can do is that, okay, we write a phi, which is a proxy of this phi divided by Li, and require that if I do phi restricted to field I plus 1 M, this is equal to L times phi I plus 1. And so this is supposed to be phi over L to the I. This is supposed to be phi over L to the I plus 1, and you multiply by L, so they're the same. So instead of having a phi, just one phi, and each time you divide by L to the I, you just remember what phi divided by L to the I is. And finally, I need to require that M to be equal to the sum of phi of M. So if you take the image of this phi divided by Li and this field M, if you take all this image in M, this will generate it. Okay. Another remark about this linearity here. Remember that when we talked about filter phi one, the phi is semi-linear action. But this here I said linear action. So linear action because we're working with k equals qp. If k is extension of QL, k is of QL. If k is extension of QL, then this has to be changed to some sort of semi-linear version. So I'm not going to do that. So that's the description of objects. It will consider, so this object will consist of, okay, first of all, it's a finite general O module. It's instead of finite dimensional, it's allowing torsions. And with a filtration, where the filtrations are given by the direct summands. And also I require Hochschild weights to be between 0 and L minus 2. So that's a constraint of the theory. And also, I need some sort of integral version of phi divided by L to the I. So I do phi I, which sort of describes it. And morphisms? It's basically M goes to M prime, compatible with all additional structures. So let me just emphasize the key constraint here. Let's iterate. First of all, K needs to be absolutely unramified. And of course, I can take K to be QL taking K to be QL will simplify our discussion, but somehow the generality of the theory is require K to be absolutely unramified. Secondly, I need the hard train weights to be must be in this. Okay? Or if you say, okay, maybe my K is mildly ramified. That's possibly okay if you require hard train weights to be in 0 and the p minus 2 divided by the absolute ramification degree of K. So that's still gives me L minus. So that's still okay. Great. Right. So here's a fact that this MF is in the Billing category. So you can take kernel and co-kernel of objects like so. Fully faithful covariant functor, we call D Fontaine-Lafay, going from this category filter modules to the representation of the group, but it doesn't have to be sort of free, locally free. It doesn't have to be free module overall. It can be sort of torsion representations as well. So I'm just going to write O of Gauss QL modules, continuous, so finite generated O modules, those continuous action of So this map goes as follows. It's a little bit tricky. So I myself is the first time to see it, so you don't have to. You can take it to the black box if you feel too complicated. Basically, Fontaine-Lafay defined it as a contravariant functor. So let's first of all turn it around to make it covariant by taking some sort of contracting dual. So let's take the contracting dual of this app. Okay? So when you take contracting dual, this phi action can be defined, and then the filtration can be defined. But then when you take the contracting dual, it's just a bit of a problem, because if you take contracting dual, this excuse me, the hard train weights will no longer be within 0 and the L minus 2 will be in, I guess, 2 minus L to 0 to be negative. So let's shift it back. And also the Frobenius action as well. So let's shift it back by shifting L minus 2 here. So that what this means is you twist the phi action by L to the L minus 2 and shifting filtration. By fill L minus 2. Okay? So basically shifting everything. Or you can think of this as somehow some sort of tensoring the filter phi modules associated to the cyclotomic character to the L 2 minus L or something. Or same as tensoring with somehow decrease of cyclotomic to the L minus 2. This is how you take the integral version of this and then you test it. Once you're done here, you palm this into the acres and take the divisible version of this. And then you take those which are phi-covariant, and then you take the field 0 apart. As I said, it looks very complicated. But if you somehow think about how we define the error from the filter phi module to our orientations, I'm essentially tensoring my M with decrease. And this is basically sort of essentially the same thing, except that somehow I'm doing the divisible version of this. Because over here I need to talk about torsion modules. So I do divisible version of decrease. So that's acres tensor. Except that, I mean, this is sort of, you can imagine this is essentially the same thing as what we had before. Okay. So we have a natural exact fully faithful functor. And so, and such that the essential image is closed under taking subjects, taking sub-objects, and quotients. So this is a little, as I said, this looks very complicated. But let me do something so that it looks a little bit better. So first explain the relation between this MF with the filter phi modules we talked about earlier. So if F, then this MF is a finite free whole module. Then I can tensor it with E, and this will carry phi 0. I mean, because phi 0 will act on everything. Because if you take I equals 0, the field M is M, so phi 0 will act on everything. Since it's already a finite free module over O, and then I tensor already inverting L, so I guess phi 0 will contain all the information about these sort of this phi 0. It contains all the information about these phi's. So this will carry a phi 0 and the field excited. This defines an admissible or weakly admissible, same thing, future phi module. In some sense, if your phi, well, maybe let's put it this way. so what does this sort of condition says here? If you think of sort of in the case of finite free O module. If you have something finite free O module, then that basically this condition says is that somehow, I'm going to make a remark before that. When M in MF is a finite free O module. Because finite free, I can now divide by L. Dividing by L is legitimate. So in this case, each phi I is determined by phi 0. Because, I mean, originally the problem is that this phi I restricted, so phi I will not be able to determine phi I plus 1 because you multiply by L. In general, you can't delete by L if you're in a torsion module. But if M is torsion free, then you can kill the L. Okay? So that basically says each phi I is already determined by phi 0. And the condition, the existence of phi I is basically equivalent to say that phi 0, when you restrict it to fill I of M, is divisible by L to the I. Namely that on fill I, the I filtration of this M, you can actually do a phi over L to the I. So that's to say that when you restrict your Frobenius, this is just phi. The Frobenius phi. And when you restrict that to the I filtration, this is divided by L. Okay. So right. And then you can show that with this being phi, and given the Frobenius, given the filtration, and this is a divisible filtered phi module. So that leads to an exercise. So here's a fact. That in this case, namely M is a finite free O module. Okay, you can define d function of phi of M. This can be written in a much more elegant way. This is nothing but M tensor with A crystal. Or phi, you adjust phi to L to the 2 minus L, and then take the filtration at 2 minus L. So basically, if you take decrease of, or rather, I mean, let me say it this way. So if you unwind the definition above, so in this case, it's just simply just tensor with A crys, and inverting L and then do that. So basically, the Galois representation you get, if you tensor that Galois representation with a cyclotomic character to the 2 minus L, that will correspond to this M inverting L. Going this way is a decrease. Going backwards is somehow, we don't have a name for it. This is this crystal representation attached to this filter phi module. To a filtered phi module. Okay. Going backwards. So going this way is usually decrease. So in some sense, this is truly, I guess if M is finite free O module, so what we're doing here is truly a integral version of the decrease we discussed earlier. But of course, this function we defined DFL works for torsion O modules. So that's the idea of this. Rather, you can think this sort of DFL can be thought as sort of inverse of this decrease function. So in general, I can always write an M as the co-kernel of M1 goes to M2 in this category, future modules, with both Mi all free. Then, by the exactness of the theorem, the representation associated to this M is just the co-kernel of EFL of M1. In the sense that somehow, if each of the Mi is all free, and therefore, this is essentially, you can take the filter phi module associated to that, you get a Galois representation with QL coefficients. And then somehow Mi will correspond to a lattice inside of that. So now you have sort of M1 and M2. You have two lattices in the corresponding crystalline representations. The co-kernel of that will be the Galois representation attached to this M, which started with. Okay, so this is to explaining going from MF to the other side, and then conversely, for every admissible future phi module M, phi module V, there exists a lattice M inside V, such that phi M being M intersect with field I. For every dimensional filter module V with Hartree weights in 0 and L minus 2. So that's a condition we can't change. Then we can find a lattice such that when you restrict your filter phi modules to M, oh, maybe it's just stable. This and my phi, when I resist to fill IM, this will go to, well, originally it should go to M, of course, but then I can pick the lattice so that when I restrict phi to fill IM, it goes to Li of M, so that we may define phi I equals to phi divided by M. So therefore, this will give me a M in this Fontaine-Laplace category of future modules. So this is an integral version, as I said many times, this is an integral version of the future phi modules. Let's again do some examples. First, this corresponds to a cyclotomic character to the R. So now I have to be careful. My R can be only between 0 and L minus 2. So in this case, let's maybe take the integral version of this. So M being O. And the corresponding field. Basically, I can use this recipe I have over here. So field I of M is O or 0 if I is less than equal to R. If I is equal to R. That's basically the same thing as the corresponding filtered phi modules. And then remember that my phi R of field RM to M. So remember, I guess, first of all, my phi will send E to P to the, hold on a second. Sorry. I need to take a negative R. My bad. Negative R. So my phi for business will send E to P to the R. And therefore, when I restrict to the this one, so this is going to be phi divided by L to the R. L to the R. We'll send maybe times E. We'll send this E just to E. That's so. And also, you want to know what phi0 is. Because phi0 is from all M to M. And therefore, it will send this E to L to the R. Right. But also, see, I just want to point out that if you take M bar to be M, tensor with F, okay, now what's going to happen is that somehow this phi 0 all the way to phi r minus 1 will be 0 because the multiplication by L. My M bar is sort of, well, tensor with F, L is 0 there. But then phi r is the information that somehow phi r is the one that keeps the information that telling you which cyclotomic character, so which power of the cyclotomic character you're having. Typical examples for analytic K modules. Of elliptic curve E over QL. So what I do is I take TL E inverse limit and this will be roughly speaking ZL squared, but this will carry, this is now canonical isomorph to ZL squared. This will carry the action of the Gauss group of QL. And so this will correspond to maybe I should say E over. It's a total good reduction, so E over ZR. So this will correspond to a future phi module. Excuse me, so Fontaine-Lafay module, or like this FM. So this will have the typical shape will be of the following. So this M will be your sum of two things. We may as well just sort of take the filtration as adapted to the basic we have over here. So that makes sense. Remember that for the curves, the tape modules have wait. So this M will. Dual of this. Okay. There's a normalization issue, right? Or equivalent maybe fixed by minus 1. Okay. Anyways. So hard chain weights are 0 to 1. So you can always adjust filtration to be as so. So two typical situations. If E is ordinary, or maybe I should say E is ordinary at P at L, then this is phi0 from M to M. So it looks like something like L alpha and alpha equals, where alpha is some error in the because the determinant has to be L. E1 is in the field 1, so it has to be completely divided by L. So therefore, somehow phi1 from ZL of E1 to N will have to, somehow this is basically send E1 to R for E1. So this corresponds to the ordinary situation. If this E has a supersingular reduction at L, this phi0 will look like L here and 1 here. Will be sort of the opposite here, or maybe negative 1. What typical looks like that. And in this case, somehow, if I do phi1 of U1, I guess the point is somehow I have a way to adjust this E2 here to scale it so that phi E1 is precisely equal to E2. So let's talk about, get to the last topic of this. How have we done? Deformation of how to deform this. So remember that we So the idea is that we start with some rho bar here. Typically this will correspond to some M bar. Right? Now I want to deform my rho bar. I can put down sort of standard frame deformation, but then we'll get all the possible lifts of this, all sort of not very nice representations. Sort of crazy chaotic representations I can get. Anything. But then I want to only deform to those crystalline representations. So for that, over here, we can't quite control very well. Instead, instead of deforming the Galois representation, I deform the corresponding Fontaine-Laffite module. So the idea is that instead of deforming rho bar, I guess I want to say that I'm talking about local representation. We deform the corresponding Fontaine-Laffite module. So that after we deform Fontaine-Laffite module, because Fontaine-Laffite module eventually will always give us crystalline representations. So in some sense, all we're going to get is that somehow, if you have this X rho bar here to be the deformation space, then I will see that the subspace parameterizing all the crystalline representations. And also, we also know that crystalline representations, for crystalline representation, we can always find a lattice that which sort of come from the Fontaine-Laffite modules. So therefore, we really computed exactly the crystalline deformations of this rho bar. So that's here. So I start with just like the usual deformations here. I start with the Fontaine-Laffite module, such that M bar is an F vector space of formation. Here's the assumption. I mean, this is not very essential, but make our life a little bit easier, so I'll just assume that. Assume that for each I, dimension of the graded I plus the So namely, each hot tip weight will no longer have multiplicity. The multiplicity at most one. So then I can let lambda 1 strictly less than this. Oh, excuse me. Lambda n denote the different hot tip weights. I'm a little nervous. Maybe not as soon. Later. Okay. So later as soon. For now. For now, let's just maybe. Okay. So let's assume this later. Okay. I've decided this somehow. We're going to assume this later because I want to explain something to indicate the issue of somehow to discuss the case when hot tip weights might have multiplicity. What kind of issue it will bring us? So nonetheless, let lambda 1 to lambda m denote that this different hot tip weights. In the sense that if the two hot tip weights are the same, I just pick one. So I have an m here. M is nothing for m. If I assume this first thing, namely hot tip weights doesn't have multiplicity, then m equals n. Okay? So I want to choose a basis. Oh, shit. Then there's a problem here. Once I did this, when I remove that hypothesis, I'm in a little bit of trouble. How do I do this? So, okay. So the field lambda m is going to be f times En. So if I have the multiplicity, okay. So let's assume this, and keep in mind that how this will change our discussion. Sorry. I apologize for the change. Okay. So then now each graded piece will have dimension 1. So this field lambda n being the largest filtration will have this. And then field lambda n minus 1 will be two-dimensional. So let's say I pick a basis n minus 1, and so on and so forth. This will the whole thing. Okay? So now you kind of see that, suppose that we don't have this hypothesis, so each time you may not just sort of add one, basically you may not have a full flag of this vector space. You just have a partial flag of the vector space. So that's the only difference. But somehow in terms of writing it's a bit annoying. So now I want to consider a function. A kind of a frame, again, some sort of frame deformation function. Oh, sorry, from the complete local algebra to this. Now I want to send A to the following things. M lambda 1, lambda n of the form so this is some sort of framed, you can think of it as some sort of framed Fontaine-Lafayette module, in the sense that I frame the lambda ith filtration to be precisely giving it some basis. And then I require my phi to really lift the corresponding. Huh? Oh, that's fine. Let me just write it down. Suppose I don't have to write it. Not right. Maybe call it phi bar. Okay. So I started out with some phi bar, and then this phi will lift that. Okay? So it's a frame deformation of this Fontaine-Lafayette module. So theorem, this deformation is represented by the following. Very simple. Power series of n square variables. Proof. Let's look at the conditions for this being, I basically practically write down a Fontaine-Lafayette module in the sense that this filtration of M, it looks like so, and you show the filtration is a direct summon. That's true. Except I have to verify that, except I have to verify that somehow the phi action is sort of compatible is sort of nice, right? So what are the new information here, anyways? So the only data for an object we have here in this deformation function. It's basically the phi lambda i's, right? I mean, the filtration is already kind of determined, and even gives it's even given the basis. So what do I need to? What do I need to determine? Anyways. So we need to record the following. So I need to record the largest one. So phi lambda n. I need to record phi lambda n of En. The column vector. I mean, it's a little bit annoying. I mean, because my filtration is decreasing. So I guess I'm going to order my basis as En minus 1 all the way to E1. And nonetheless, so this is phi lambda n En will map to some column vector, right? So once this is done, if I want to know phi lambda n minus 1, how this is defined. So this is defined on Aen direct sum Aen minus 1. Right? But by the compatibility with phi lambda n, so this part, you already know how phi lambda n minus 1 should act on it. Basically, it's equal to sort of L to the lambda n minus 1 times this. So this is over here. This is the same thing as sort of L to the lambda n minus 1 times phi lambda. So this part, you already know how to define that. So only sort of the part you don't know yet is this sort of En minus 1. Before that. So this is a column vector. Right. So you continue this discussion. So now you see that you have to understand what this thing is. and so on and so forth. Right? So let's make them a matrix. So set F is a terrible notation. I can't think of a better notation though. I'll put this as a column. So put this sort of column vectors as the columns of this matrix. So this, first of all, this is a matrix with coefficient A, because these are column vectors. Right. Now we can say about these. Let's see. What can we say about these? Claim. Well, first of all, I guess F modulo next idea of A must be the F bar, where F bar is defined using the original F bar. And claim that somehow this condition sum of phi fill I of M equals M is in fact equivalent to phi F being in matrix, invertible matrix. Okay, why is it so? Because if you look at the left-hand side, this is precisely spanned by these phi lambda n, phi lambda n minus 1, n minus 1, and so on and so forth. Right? I mean, of course, I can say, okay, of course, phi lambda n minus 1 starts from a two-dimensional space. But when you use this to set En, it's just basically the same thing. Will have the same image as phi lambda. So therefore, it's essentially using phi lambda setting En, and then phi lambda n minus 1 setting En minus 1, and so on and so forth. So therefore, this huge sum is precisely spanned by these column vectors. And if you want these column vectors to generate the entire n-dimensional space, that's basically equivalent to say this matrix is invertible. But then we know that it's the same thing as F bar being invertible. Right? But excuse me, F bar in A bar and A. But we know that we started with F bar, which is a function of 5 modules, so this is automatically true. I mean, in that case, the sum of this thing is, because this is the same thing as the sum of phi bar I of fill F bar equals F bar. Because we started out with the function of 5 modules, so this must be true, and therefore this is true, and this is true, and therefore this is true. So therefore, this condition on the function, on this sort of whatever lift you have, being a function of 5 module is automatic. So this is. In other words, we have no constraint whatsoever. We can lift phi whatever I want. So basically, so all we need to do is to lift this F bar, basically arbitrarily. Whatsoever, there's no constraint whatsoever. So that means, this has n squared entries, so definitely represented by the formal power series x1, so xn squared. No constraint whatsoever. Okay. So now, let's go back to the original question of, let's think about the case where, what happens if each of the gradient is not one-dimensional? Well, if each gradient is not one-dimensional, I mean, if you look at the proof, right? You just fix, for each filtration, you have different, more basics in some sense. And this is okay. And over here, you just have more bases to have if to different columns, right? So nothing changes. So this statement still follows true. This is still true without hypothesis on sort of dimension of the graded piece. Okay. So the next thing I want to discuss is how this filters. So this is a framed one. But what are really the ambiguity? I mean, somehow, like when we deform this way, it somehow fixed my filtration must take this form. And I'm really deforming the matrix of phi. But of course, in terms of isomorphism classes, we only know the filtration, but we don't know precise basis. So, what we do know is that there's an action. There's a natural action. Right. Let's maybe write it in a more elementary way. So there's a natural action of the following group. All this deformation. Okay? Or if you want to write it more formally, this is the action of the Borel. Of somehow that you take the upper triangle of the I guess you take B to be the upper triangular matrix. Think of it as an algebraic group, and then you complete it at 0. So this will act on stuff of R and frame. What it does is that now it will changing. What it does changing is En to En prime being some scalar times En. Because if you field lambda n is a vector space given by, so it's a free module over En, but I can choose a different basis. In the same way, I can have En minus 1 change to En prime minus 1 equals to star En minus 1 plus something times En. Because I only know the filtration, I don't quite know sort of which basis I should choose, and so on and so forth. So let's make this action a little bit more explicit. So say a new basis. Say we take sort of the form. Time P, where P is upper triangle. So P belongs to. But pick a new basis. Then, right. Then remember that I record my phi action as so. So let's see. So let's maybe just, because this is torsion free now. So let's just look at how phi 0 would act. So originally, let's look at phi 0 acts on the basis U1 through U1. So what was that going to give you? It will give you U1, En, U1. And the first column, you're going to put what this phi would act on En. So maybe I should say. So I should be putting phi lambda so how phi 0 would act on here, right? And then phi 0, how that would act on En minus 1. Phi 0, how that would act on E1. Okay, but how does phi 0 act on En? Well, that's going to be p to the lambda n times phi lambda n En. So this is p to the lambda n minus 1, phi lambda n minus 1, En minus 1, and so on and so forth. So let's rewrite it in a more reasonable way. So this is, think about this is what we have over here is the first column. It's the same first column as f, but you multiply with p to the lambda n. And the second column is precisely the second column of f, multiplied by p to the lambda minus 1. So what you have is this f times this matrix. Okay? Right. So now let's do the change of basis. So if I have this, I should be getting an f prime, a different one. Okay? Whereas the right hand side will be equal to En U1 times P times f prime of P to the lambda. Whereas the left hand side will be phi applied to, will give me phi applied to En E1, then I right multiply with P. Because E primes are the E's times P. And this phi of this is equal to En E1 f of P lambda n P lambda 1. So what we'll see here is that this must be equal to this. So just to explain what the action is, so this basically says that somehow my f prime is equal to, let's see, move P inverse to the other side, f of oops, let me just use this P inverse. So in other words, this action does the following. It looks like conjugating your matrix or limit f by p, but it's not conjugating, it's sort of twisted conjugating. On the left hand side, it's multiplied by inverse of p, but on the right hand side, it multiplied with p times, so conjugated by this thing. What this conjugation does is that originally, supposedly your p is pij, and then what's going to happen is over here is this is equal to, just maybe write the n equals 3 case. So you can have p11, p22, p33 as this, but p12 will be multiplied with L to the lambda 2 minus lambda 1. And this p13 will be multiplied with L to the lambda 3 minus lambda 1. And this p23 will be multiplied with L to the lambda 3 minus lambda 2. So it's some sort of twisted conjugation action. So again, going back to my earlier comments about hard-type weights allowing to be not sort of multiplicity 1. So in that case, the same discussion is still the same, except that the action is no longer by the Borel group, sort of the upper triangular matrices. It's given by the parabolic subgroup, sort of block upper triangular matrices. we should somehow, these are just framing. So it's natural to consider somehow xm as a quotation mark, since we don't know but of this. We're talking about frame the deformation. And then I quotient out by this formal completion of B at, or maybe I should say B1. It's really complete. And what's the dimension of this guy? The dimension should be, dimension over O should be equal to n squared, what we had earlier, minus the dimension of the upper triangular matrix. So that's, so you're left with, if you kill the upper triangular, you get somehow, dimension-wise, you get a strict lower triangular. So that's going to be n minus 1. But if we don't have the multiplicity 1 for Hochschild weights, the quotient here will be, you'll be quotienting on the sort of block diagonal, sort of block upper triangular matrix. So this dimension will be smaller. Somehow, expectedly, we should get a natural embedding of xm embedding into x row bar, where the row bar is, you can think of this as quantum of phi. So instead of deforming, if you deform, the right hand side is a deformation of the Galois representation. The left hand side is a deformation of the quantum of phi logics. In the sense that the deformation of quantum of phi logic will always give you a crystalline representation. So this should be thought of as a subspace of this full deformation subspace local row bar, where the representation is crystalline. In other words, what we're writing here is that somehow I have somehow spuff Rm. This will embed into spec of R row bar over PT dot. I have some sort of embedding like so. So let's do a dimension count. So next lecture I will explain why somehow we care so much about this sort of dimension numericals. Which of course on one side is very important for Taylor-Wells method to work. On the other side, it really carries some sort of meaning, algebraic geometric meaning. So when n equals 2, somehow we talk about this x row bar. This x row bar when it's better to sort of fix determinant. So this one has dimension over O being 3. Okay. So this is basically the order diversity of the Eichel representation. Whereas this xm, by the dimension formula over there, this guy has dimension O being 1. So somehow I want to convey the following, in the sense that within this sort of three-dimensional deformation space of the residual combination, only one-dimensional is crystalline. So these representations are very, very rare compared to all possible representations. Right. So I guess I'll stop here. And the next time I will talk about sort of what kind of representation we see geometrically in algebraic geometry and such. And then eventually I want to explain. So now maybe just say a little bit more. So I have the Galois group of Q. So now suppose I have some residual Galois of the global Galois group. Okay? So now I have my x row fixes some determinant, which is sort of not very important. And I map it down to a product of x row bar V. So is over QP, so yeah, still B, right? But not the product of all of these things. The dimension. Let's maybe if I count dimension right, so count to be 2, say. So dimension over here, and also I want to be odd. The complex conjugation. I'll say why I need this condition. Suppose we have all these conditions. This guy has dimension 2. We talk about somehow the relative dimension is at least 0 in a stacky way. But anything that comes from geometry tend to look like, so at least somehow at where B equals P, so B not equal to P, I take whatever I want, but then at rho bar P, I want to take sort of a function of phi. So originally the corresponding guy here is 3-dimensional. This guy is 1-dimensional, so this is codimension 2. So when I take fiber product, I look at determinant this one, where I have function of phi at P. So this guy has relative dimension 0 over O. Okay. So that will be the picture we're going to discuss next time. In the sense that everything from geometry, so everything from geometry, it tends to have sort of let's say locally, its image should roughly land in here. And therefore, if we look at sort of all deformations with this local function Lafayette condition, such global deformation will have relative dimension 0 over O. Namely, it will be something, you should imagine, finite over O. So that means fixing local conditions, you should imagine that there are only finite many sort of true sort of geometrical objects which satisfy these properties. In a sense, instead of having found a sort of representation satisfying these properties, you only have sort of